We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will continue our study of rotational motion. In particular, we will first prove a very useful theorem that relates moments of inertia about parallel axes. We will then move on to develop the equation that determines the dynamics for rotational motion. In so doing, we will introduce a new quantity, the torque, that plays the role for rotational motion that force does for translational motion. We will find once again that the rotational analog of mass will be the moment of inertia. A couple of pre-lectures ago, we showed that the total kinetic energy of a system of particles in any reference frame is equal to the kinetic energy of the center of mass of the system, defined to be 1/2 times the total mass times the square of the center of mass velocity, plus the kinetic energy of the motion of all of the parts relative to the center of mass. For a solid object, the only possible motion relative to the center of mass is rotation. Therefore, the kinetic energy relative to the center of mass is just equal to 1/2 times the moment of inertia about a rotation axis through the center of mass times the square of the angular velocity about the center of mass. We can use this result to calculate the moment of inertia about a chosen axis if the moment of inertia about a parallel axis that passes through the center of mass is known. For example, here we see the thin rod from last time rotating about an axis at a distance d from the center of mass. We can describe this motion as the center of mass rotating about the axis with angular velocity omega plus the rod rotating about its center of mass with that same angular velocity omega. Thus, for every rotation the center of mass makes about the axis, the rod makes one revolution about its center of mass. We start from our previous result that the total kinetic energy about the chosen axis can be written in terms of the moment of inertia about that axis. Now we know this kinetic energy must be equal to the sum of the kinetic energy of the center of mass and the kinetic energy relative to the center of mass. Now the velocity of the center of mass in the lab frame is just equal to d times omega. And the kinetic energy relative to the center of mass is just equal to 1/2 times the moment of inertia about this parallel axis times the square of the angular velocity. We can cancel a factor of 1/2 omega squared from each term in the kinetic energy equation to determine that the total moment of inertia about the chosen axis is just the moment of inertia about a parallel axis passing through the center of mass plus the moment of inertia of the center of mass treated as a point particle about the chosen axis. This result is known as the parallel axis theorem, and it will prove to be very useful in the next few lectures. You can verify that this parallel axis theorem predicts the relationship we obtained last time for the two moments of inertia for a thin rod. We can now use this parallel axis theorem to calculate the moment of inertia of a dumbbell made up of two solid spheres connected by a solid rod about an axis that is perpendicular to the rod and passes through its center. We'll start by using our result from last time that the moment of inertia of the dumbbell about the given axis is equal to the sum of the moments of inertia of its components, the rod and the two spheres, about that same axis. To find the moments of inertia of the spheres about the axis through the center of the rod, we will apply the parallel axis theorem we developed in the last slide. Namely, we know from last time that the moment of inertia of a solid sphere about an axis passing through its center is equal to 2/5 times the product of its mass and the square of its radius. Applying the parallel axis theorem, we see that the moment of inertia of each sphere about the given axis is just equal to 2/5 mr squared plus m times L over 2 squared. To find the total moment of inertia of the dumbbell, we just add the contributions from the two spheres to the moment of inertia of the thin rod about its center to get the result shown. So far in our study of rotations, we have made explicit connections to the kinematics of one-dimensional linear motion and the concept of mass. We will now use Newton's second law to develop the equation that describes the dynamics of rotations. Here we see a point mass constrained to move in a circle being acted upon by an arbitrary force F. We choose to use polar coordinates, r and theta, to describe this motion since r will be constant. Since the mass is moving in a circle, we know there must be a component of the net force acting on the mass that is radial to supply the radial acceleration, v squared over r. In addition, there may be a component of the net force that is tangential, which will result in a non-zero tangential acceleration. This tangential acceleration is simply related to the angular acceleration of the rotation. We know that the rotational analog of mass is the moment of inertia, which in this case is just equal to the product of the mass of the particle and the square of its distance from the axis of rotation. If we now multiply both sides of our force equation by this distance r, we find that the product of r and the tangential component of the force is equal to the moment of inertia of the object about the rotation axis times the angular acceleration. The right-hand side now looks like a rotational version of Newton's second law, namely the product of the rotational mass, the moment of inertia, and the rotational acceleration. It would be natural to identify the left-hand side of this equation as the rotational force. Indeed, we will identify the product of the tangential force and the distance between the application point of this force and the rotation axis as the torque, the quantity that plays the role of force in rotational dynamics. In the next few slides, we will formally define the torque as a vector quantity and will arrive at a general vector equation that is the rotational version of Newton's second law. We've just seen that a torque, the product of a tangential force and the distance between the application point of this force and the rotation axis, produces an angular acceleration. As a concrete example, here we see the overhead view of an open door. Now, to close this door, you need to push on it. Here we see a force F being applied a distance r from the hinge. The door is heavy and barely moves as you push on it. What would you change about the way you are pushing in order to close it quicker? Your intuition tells you that you would either push harder or you would push on the door at a point further from the hinge. You would certainly not try pushing closer to the hinge, and you would also not change the direction you are pushing to be more parallel to the door. In other words, the biggest effect you can have on the door is to push on it as hard as possible in a direction perpendicular to the door at a point far from the hinge. The equations we derived on the previous slide tell us exactly the same thing. We expect the angular acceleration to be biggest when the torque is biggest. In other words, the door will close fastest when the torque is large. The torque is largest when the distance r between the axis and the perpendicular force is biggest and when the perpendicular force itself is biggest. If we push parallel to the door, there is no perpendicular force component and we don't expect the door to start moving at all. On the next slide, we will generalize this description of rotations by defining torque, angular velocity, and angular acceleration as vector quantities. Here we see a spinning top. So far, we have described this motion in terms of one-dimensional variables, the angular displacement, the angular velocity, and the angular acceleration, all defined relative to the axis of rotation. We will need to generalize this description to 3 dimensions when we allow the direction of the rotation axis itself to change. If a rotating object is viewed in a reference frame in which the rotation axis is perpendicular to the screen, it is convenient to define a counterclockwise rotation as positive and a clockwise rotation as negative. We adopt this convention in order to match the usual measurement of the angle theta relative to the x-axis in a right-handed Cartesian coordinate system. There is a simple rule involving the right hand that can be used to define the directions of the angular velocity vector. Namely, if you curl the fingers of your right hand in the direction of rotation of the object, your thumb will point in the direction of the angular velocity vector of the object. In other words, if some object is spinning in the counterclockwise direction in the xy plane, curling the fingers of your right hand in this direction results in your thumb pointing in the plus z direction, which we define to be the direction of the angular velocity vector. Similarly, if the object is rotating in the clockwise direction, the same exercise results in your thumb pointing in the minus z direction. We use the same right-hand rule to define the direction of alpha, the angular acceleration. For example, if the angular velocity increases in time, then the angular acceleration vector has the same direction as that of the angular velocity. If the angular velocity decreases in time, then the angular acceleration vector has the opposite direction as that of the angular velocity. One nice feature of using the right-hand rule to define the direction of vectors in systems involving rotation is that these vectors then do not rely on the choice of a coordinate system at all. The rotation vector becomes a property of the object itself. On the next slide, we will develop the vector equation that describes rotational dynamics. On the last slide, we defined angular velocity and the angular acceleration as vector quantities. We will now define the torque as a vector quantity and obtain the vector equation that determines rotational dynamics. We have shown that the magnitude of the torque is given by the product of the length of the line connecting the axis to the point where the force acts, R, and the component of the force F that is perpendicular to this line. If we define theta as the angle between this line and the force, then the perpendicular component of the force is just F times sine of theta. If we consider the line connecting the rotation axis to the force as a vector, then the magnitude of the torque is given by the magnitude of the vector F times the magnitude of the vector R times the sine of the angle between them. We write it in this way because there is a mathematical construct called the cross product that has exactly this same property. Namely, given two vectors A and B, the magnitude of A cross B is given by this same form. The direction of A cross B is perpendicular to both A and B and is given by the right-hand rule. If you point the fingers of your right hand in the direction of A and curl them toward the direction of B, then your thumb points in the direction of A cross B. Using this definition of the cross product and what we already know about the right-hand rule, we can write a vector equation that neatly summarizes everything we know so far. On the right-hand side, we have the angular acceleration vector, whose direction is found by applying the right-hand rule. On the left-hand side, we have the torque vector, whose direction is also found using the right-hand rule. In the example shown, we see that the directions of the torque and the angular acceleration are the same. They are both parallel to the rotation axis pointing out of the screen. This equation, the net torque about an axis is equal to the product of the moment of inertia about that axis and the angular acceleration, is totally general. This equation is just Newton's second law applied to a system of particles in rotation. We conclude with a brief discussion of the main points of this prelecture. First, we proved the important parallel axis theorem, namely that the moment of inertia about a chosen axis is equal to the moment of inertia about a parallel axis passing through the center of mass plus the moment of inertia of the center of mass treated as a point particle about the chosen axis. Second, we introduced the concept of torque, the concept that plays the role for rotational motion that the force does for translational motion. Namely, we defined the torque generated by a particular force F about a chosen axis to be equal to R cross F, where R is the vector drawn from the chosen axis to the application point of this force. Third, we used Newton's second law to derive the general equation that determines the dynamics of rotational motion. In particular, we developed the relation that the net torque about an axis is equal to the product of the moment of inertia about that axis and the angular acceleration.